Hello, sir. My name is Shubdeep Gupta, and I'm here with my friends Meet Soni and Geetika Sharma to present the presentation on the topic Hebbian Learning. So, let's start with the introduction. Hebbian learning is a term derived from the work psychologist of Donald Hebb in 1949, and it represents a key concept in the realm of deep learning, drawing inspiration from the working of human brain. So, Hebbian learning is a synaptic plasticity rule, a set of principles that govern how the strength of connections between neurons evolves over time. So this shows the essence of Hebbian learning lies in the fundamental position, like cells that fire together wire together. When two neurons are activated simultaneously, the connection or synapse between them strengthens. So let's come to the next slide. Mechanism of Hebbian learning. So let's delve into the mechanism through which neurons communicate and adapt. Neurons, the fundamental units of our neural network, communicate through synapses, and these synapses are the vital connections that enable the transmission of information between neurons. Like you can imagine two neurons, A and B, connected by a synapse, and Hebbian learning posits that when neuron A consistently and repeatedly triggers the firing of neuron B, the connection between them strengthens, and this strengthening of synapse is a direct result of the synchronized activity of these neurons. For its applications in the realm of artificial neural networks. Inspired by the working of the human brain, artificial neural network incorporates Hebbian learning principles to enhance its learning capabilities. So, in machine learning, Hebbian learning serves as a crucial mechanism for neural networks to adapt and fine tune their weights based on the input patterns. So, one significant application of Hebbian learning is artificial neural network and its contribution to unsupervised learning. Unsupervised learning involves abstracting between patterns and information from input data without explicit labels. So, Hebbian learning allows neural network to discern and learn these patterns autonomously. So now, Geetika will tell you how all this implementation in perceptron will happen.
A perceptron is the simplest form of a neural network. It is the basic building block in the field of artificial neural networks. It consists of input nodes, weights, a summation function, and an activation function, and an output. The input nodes receive signals. Each connection has a weight that adjusts during the learning. The summation function calculates the weighted sum of inputs. The weighted sum is then passed through an activation function, such as step function, sigmoidal function. If the sum is above a certain threshold, the perceptron activates, otherwise it deactivates. The perceptron learns through a supervised learning process. The weights are adjusted during training based on the error in the output. The learning algorithm aims to minimize the difference between the predicted and the actual output. If the perceptron produces the correct output, weights remain unchanged. If the output is incorrect, weights are adjusted to reduce the error. The adjustment is proportional to the input and the error. Here is a simple procedure for applying the Hebbian rule in a neural network. First, the weights and the bias are set to 0. For each input vector S and the target, we repeat the following steps. We set the activation functions for input units with the value from the input vector. Each element X represents the activation of an input neuron. We set the corresponding output value to the output neuron, that is y is equals to t. This means that the output of the neural network is set to the target output. We update the weight and bias using the Hebbian learning rule. It suggests that if the input neuron is active and the output neuron is also active simultaneously, then we strengthen the connection or increase the weight. The weight update equation for each I would be something like Wi new is equals to Wi old plus the learning rate xiy. The bias is also updated similarly, adjusting it based on the activations and the target output.
Let's simplify the limitations of Hebbian learning. The first one is reinforcement of existing patterns. Hebbian learning strengthens connections in the brain when neurons fire together. While this helps keep things stable by repeating what's already known, it can make it harder for the brain to learn the new stuff. Imagine if you always practice the same dance move and never tried something new. You'd really get good at that move but might struggle to learn different ones. The second limitation is absence of inhibitory neurons. Hebbian learning mostly thinks about how excited neurons get and doesn't pay much attention to the neurons that calm the things down. In the brain, some neurons help balance the excitement, like how brakes works in a car. Without considering this calming neurons, things might get too excited and out of control, like a car going too fast without brakes. The final limitation of Hebbian learning is lack of specificity. Hebbian learning isn't picky about which connections it strengthens. It treats all connections the same, even if they might not be very important. It's like practicing a song on the piano but accidentally pressing all the keys, including the wrong ones. This lack of precision can make the brain less efficient because it reinforces connections to the things that doesn't matter, like practicing the wrong keys instead of the right ones. Concluding the presentation, imagine Hebbian learning as the basic blocks of how computers learn stuff. It's like learning how to ride a bike. It's good for getting started, but it's not great for everything. Sometimes it struggles with things like learning new tricks or riding in tricky places. To help computers learn better, scientists are looking for ways to add extra tricks and skills to Hebbian learning. They want to make it better at handling different kinds of learning challenges, like not just riding a bike but also learning skateboarding or even driving a car. So they are working hard to upgrade how computers can learn so they can do a lot more things in smarter ways.